All right, guys, position, velocity, and acceleration. We are going to just review some things that we already know. S of t is what we've been using for our position function. Sometimes it'll be x of t, sometimes h of t, but it's relative to a position. Our velocity is the derivative of our position function. And last but not least, our acceleration would be the derivative of the velocity, or if you think about it, it's the second derivative of your position. That is nothing new. We've already talked about this. What we can add now is that our velocity function then would be the integral of the acceleration function. Right? I can work backwards now. So if I give you acceleration, you could find the velocity. And if you knew the velocity, you could go back to the position function by integrating the velocity function. Some cool notation. It would also be the second integral, the double integral of your acceleration function, because you're going two steps backwards, right? You're taking two antiderivatives. I don't know that we'll ever use that notation, but it's kind of fun to see that it exists. So here's an example. They're going to look a lot like what you had before. It's just the order that things are going in. It says that we have a ball thrown upward with an initial velocity of 64 feet per second and an initial height of 80 feet. So they are giving us here a couple of points. Our velocity at time 0, initial velocity, right, time 0, is 64 feet per second. Oh, I think my units are off on my acceleration. And my position at time 0, right, was also given. It was 80. If you think about the example that we just did together, these are the two conditions that they're giving you to help you find those plus c's. These are those specific values that are going to give you an exact answer instead of just a generic antiderivative. Use the position, the acceleration then is a function. Acceleration is negative 32, and it's feet per second squared. Notice that it is a constant. Well, if we want to find the position function as it states here, then I'm going to have to just go backwards twice from that acceleration. So I can take and find the velocity function by integrating that acceleration function. So we're going to integrate a of t, which in this case is the integral of negative 32. We'll call it dt for time. And if I integrate a constant, I'll just get negative 32 times t plus c. I need to find my c before I can move on so that I don't just have that antiderivative. I need to know the exact value, and I'm going to use my velocity, my initial velocity at 64. If t is 0, right, then I know I'm supposed to get 64 for the velocity. So that would mean that negative 32t plus c is equal to 64. I should have gone ahead and plugged in while I did that, right? My time is 0 because it's my initial velocity, and so my c is simply 64. It's really nice when they give you the initial velocities or the initial positions, because plugging in 0 is really easy to do. Once I have my velocity function, right, we could rewrite that then using the antiderivative, negative 32t plus 64. I could go ahead and solve for my position function. Right, so I'll be integrating that negative 32t plus 64 with respect to time. And that is going to give me what? I'd have negative 32 times t squared over 2. I'll have a 64t and a plus c. Let me rewrite it a little bit neater. It's kind of fallen off the page there. My position function then is going to be negative 16t squared plus 64t plus c. And using that specific value, right, we know that when t is 0, I'm going to end up getting 0, 0, and c. And I already know that when time is 0, I'm supposed to have a position at 80 feet Therefore, C is 80. And I can go ahead and come up with my position function, negative 16t squared plus 64t plus my 80. They had asked for the position function. For those of you who are in physics, or even those of you who are in our class, you have probably seen this before, right? It's always half of your gravity plus the initial velocity times time plus the initial position. This integration here shows exactly why that's true. We could do it with, an A and a B as our initial velocity and our initial acceleration. We could come up with those values specifically for that formula. So that answers the question at the top. Find the position function given the height s as a function of time. When does the ball hit the ground? Well, how do you figure out when the ball hits the ground? That would be the place where your position, right, is equal to 0. The ground is always our 0 here. And if you didn't have a calculator, you could actually factor this one out. I've picked some friendly numbers for you. We're going to get minus 4t, and we're going to get a minus 5 equal to 0. And I'm running out of space here. Negative 16, it'll be t. I want to multiply the negative 5, add to negative 4. So minus 5 plus 1. And my solutions are either 5 seconds or negative 1 second. I don't have a clue what that would look like. You can't throw back in time. So the answer here is that you needed 5 seconds. Right? It was actually just some algebra for that last piece. Your homework for today then to practice for these sections comes from both your textbook, probably some particular solution problems in there, maybe a couple word problems. And then I've added on a couple of word problems on the back side of this to save paper. I just got it on the back of your notes. And you'll be able to find the solution sets online so that you can check your work. Tomorrow, Friday, at least for this year, expect to come in and we'll have some more mixed practice with just antiderivatives in general and word problems probably as well. Thanks for listening.